Good afternoon, everyone. Welcome to week 2 of the technical lecture series for first year degree students. This is the chart that I showed you in the introductory lecture, which is the sort of, if you like, the syllabus, the areas that we're going to be covering this year. And as you can see, or can I remind you, that the chart is broken down into two principal sides. One is structure and form, and the other is climate and shelter. And structure and form is again broken down into 3 columns: physics, elements and logic. So today we're going to start with the first column, structural physics. We are going to look a little bit on materials science and the properties of materials and reactions. Materials technology, in terms of this area here, we're going to focus on next term, so I'm not going to be talking specifically about these materials today, although we will of course have to touch them or refer to them as the lecture series progresses. And then we will look at these last 2 areas of loads and stability. So structural physics, as I said, we will start by looking a little bit at materials science and the properties of materials. Bending, which is critical because when any materials is subjected to any kind of load, it's a force, and that force the material will react to, and materials that we use in construction tend to react by bending, and it's the control of that bending or the limiting of that bending that is critical to our how we use materials in construction technology. The integrity of a structure, in other words, how it can be prevented from failing under certain kinds of loads, principally involves bracing, which I will explain. And finally, the actual stability of the structure, how it keeps its verticality or not, as the case may be. We shall discuss that. So materials science. I'm going to read this. As I said, I don't usually read from PowerPoints, but it's important that this is understood. Structural form. All objects, this is as I just said, have an underlying structure that maintains the form of the object when it is subjected to forces. The forces act upon the object, and the object reacts according to the properties of the materials from which it is made and the way in which they've been shaped and assembled. Stress is the term used to describe the forces acting on a material or structure, and strain is the term used to describe the material or structure's response to those forces. Now, I should start off by saying, of course, that the primary force that we are resisting in all structures is that of gravity. And gravity, as I'm sure most of you are aware, is a force that is effectively trying to distribute everything on the planet to the center of the planet. It is a force that is pulling all objects towards a singularity, if you like, at the center of the planet, and we have to react to that. There are 2 ways in which almost all materials react, and one is in compression and the other is tension. In other words, a material can be pushed, forced by pushing, or a material can be pulled. Now, if we just look at stress and strain at the bottom there, stress. Forces can act on materials in one of 2 fundamental ways. Yes, I've just said that. These applied forces are described in physics as stress, which is measured as the force per unit area across any given cross-section of the material. So stress equals force over area. Strain. Materials use their internal structures to resist force. Every material reacts to stress by distributing it in such a way that there's an equal balance of internal forces, and the result is strain, which in fact is a change in the form of the structure. As I said, structures do bend, measured as the fractional extension perpendicular to the cross-section. So if we look at a simple column, let's say, that we have here on the left on compression, as you push down on the column, in an exaggerated form, the column begins to deform and the outer side of it begins to stretch. By stretching the outer side of the column, those parts of the column are actually going into tension. Now, the opposite is happening when you're pulling on a column. If you're pulling on it, the outer sides of the column bend in and start to compress. So bending is the result of a material deforming itself under stress. And what's critical when we're designing construction elements is the cross-sectional shape of the material. And it's fairly obvious, I think, from these diagrams. if you push down on a flat shape, it will deform. By simply turning that same cross section, that same shape through 90 degrees, it will no longer deform. And the same is true in the column on the right, except you're not putting it through 90 degrees, you're equally distributing the load. Effectively, you're turning what was a rectangle into a square. Here's a fairly simple illustration of that. Okay, you can see what's going on here. The piece of timber is going into bending once it's loaded because it's got a very thin cross section. The moment you change that cross section, it is better able to resist the load. What's happening in reality in that beam is that as you're pushing down on it, as I said, the top part of the beam is being compressed and the bottom part is being put into tension. Now knowing that the bottom half of the beam is being pulled and the top half is being compressed is very useful to us when designing structures. And it's a key thing to keep in mind as long as you are thinking about structural form. One of the principles that's happening here is that the span, if you like, of if you consider that beam as a simple bridge, that the span of it is related to the height of the beam, and it's called the span, I beg your pardon, to the depth of the beam. So it's called the span to depth ratio. And every time you're designing a floor or a bridge of any kind or a platform that has to span from one side to another, you will get a simple rule of thumb to calculate how deep that beam has to be in terms of the distance of the span. So there's a beam that it's still slightly bending. So actually, if we didn't want it to bend at all, it would probably have to be slightly deeper than that. Now what's happening in reality here is that the compressive side, the top half of the beam that's in compression, does not want to get in contact with the bottom side of the beam, which is in tension. The moment that happens, as is happening here, the top in compression is very close to the bottom part in tension. The closer they get together, the more likely they are to fail. So obviously, if that was simply a piece of card or paper, it would fail, it would shear right the way through, because the compressive parts and the tensile parts come together, and that is a recipe for failure. So we're keeping the top part of the beam and the lower part as far apart as possible in order to prevent failure. There it is again illustrated. The top part of the beam is going into compression. It's actually shortening. You can see in this exaggerated drawing that edge is shortening. That edge is slightly lengthening. It's being pulled in tension. Compression, tension. This is a truss. I'll go into a little bit more detail, but if you've got a very large span, of course, and you want to keep the top compressed area as far away from the bottom in tension as possible, but you don't want a big heavy beam, you don't want to be that one big solid object, you can separate the two, the top rail as we call it and the bottom rail, with these little rods which are in compression as well, beg your pardon, all in compression, and these are bracing it, just triangulating it to stop the two sides, the bottom and top, from shearing away from each other. Okay. Talking of shear, there is another way in which, well, this is the way in which structures can fail altogether, where surfaces actually move towards or away from one another. So if you have a very high load at one point in a structure and the material is unable to resist that, it will actually deform to such an extent that the two sides will actually slip away from each other and it will fail in shear. Fortunately, we know enough about materials now to be able to tell you which materials are likely to fail in shear and which aren't. To get on to structural stability, structural engineers talk about the difference between static and dynamic loads. There are lots of terms that you'll probably come across for this. Static loads are known as dead loads, dynamic loads are known as live loads, and you probably will hear other terms. The fundamental difference is, of course, the static loads or the dead loads are the mass of the building itself. All the materials that go to make that building are the dead loads of the building. The live loads of the building are anything over and above that, loads that are imposed upon the building. In normal vertical loads will be furniture, people, plant machinery, and of course external loads, which are absolutely critical, are forces such as wind and waves. Now, wind and waves are going to put a slightly different load onto the structure because it will not be absolutely vertical as pretty much all the other loads are. The only time you will get a non-vertical live load that is not either a wave or wind, possibly if you're designing an enclosure for elephants, and when an elephant sits down and leans against a wall, he's going to certainly impose a fairly heavy dynamic load. Anyway, here's an illustration of how we solve this problem of a lateral load. As you can see, simple rectangular frame at the top. If I impose a load on it from one side, in this case let's assume the wind is blowing, it's going to shear, it's going to be deform, as you can see from the upright. There are two ways in which we can solve that. Sorry, beg your pardon. One is to triangulate with a compressive strut here. The other is to triangulate with a tensile strut or wire here. So in this situation, here's the live load pressing against this edge. That force is now transferred back down into this corner where it can't go anywhere. So that can no longer deform. Let's look at the imposed load coming from the other direction in this side. What's happening now is it's pushing along there and it's pulling on this wire or rope. That is connected back to this point here. It can't go anywhere again. Its triangulation is the key. And actually, when you begin to look at structures, any structures, even a simple table, chairs, that have to withstand any kind of dynamic load that is not just purely vertical on top of it, you will notice after a while that there is triangulation everywhere. We call them invisible triangles. So that table has a little bracing structure here. See, just that little depth there. And if you look closely into that corner, what that depth is actually doing, it's triangulating the structure at that point there. So that again, if I happen to lean or push on the table this side, it cannot deform as that original rectangle did. What we're looking at here is an idealized structure. Idealized in so much it's going to resist lateral loads from any direction. And it's known as a pinwheel. It's not often that in designing architecture and buildings that you will be able to do a perfectly idealized structure, but the principle can be applied in all sorts of situations. So here's the plan, and what we've done here is we've put here's a series of columns. So instead of there being a series of simple square columns in each corner, we've elongated these columns on plan so that they're deep enough that they can create the triangulation that we need to prevent distortion under any lateral load. So again, you can see that if I'm pushing here on this corner of the building, that is that triangle there. In fact, it's a flat plane now, so it's a continuous column, but there is again an invisible triangle here that pushes down into that corner that prevents the building from moving in that direction. The same in the opposite direction. There's the triangle again, invisible. Now, if I alternate these, if I rotate these around the central point so that I have one rectangular column going in each direction, the pinwheel, I'm resisting every conceivable lateral load direction onto that building. I hope that's clear. There is another way in which structures and buildings can deform, and that is an expression known as torsion. And you can see from this diagram exactly how torsion is occurring. In other words, you're getting opposite twists on structure. Can happen for all sorts of reasons. Can be the design of the dead load of the structure puts these kinds of forces onto the structure. Could be external loads, could be either. So we have to resist structural elements deforming in torsion. So here's some examples of what we were just talking about. Here's a simple beam and column building. I'd say fairly simple. Instead of there being, say, constant triangles on every floor, as you can see, there's some major triangulation going on throughout the entire structure. Okay, these elements are bracing the structure for lateral loads, and you can see they're happening in more than one direction. They're happening on each face, if you like, of the building. a different solution to the same problem, an interesting building. In fact, unfortunately, you can't see all that anymore, but you can see this if you go down to Cannon Place, because this is on the outside of the structure. So it's expressive of the structure, which we quite like in buildings, because it enables us to understand them. There's two different solutions on each facade this engineer has designed. This solution here, as you can see, lots of struts in pure tension, rods, steel rods, in both directions, that way there and that way there, bracing that facade for any lateral loads. And on this side, some rather large and dramatic, shall we say, triangulations, which again, not one huge piece, but broken down into a couple of opposing trusses, solving the same problem. Here we are again. This is a Richard Rogers development on Bankside, just near the Tate Modern, where again you can see the bracing expressed on the exterior facade of the building. Rogers is an architect who really does like to see structure, make structure visible, shall we say. Think of the Lloyd's building in central London. Yeah, sometimes even internally you will find this bracing going on. Slightly strange. You'd think, well, why would you block a corridor? Well, there's probably going to be a solid wall at some point. And by the way, while we're looking at this, it's hard to explain without a drawing, which unfortunately I haven't got, but of course the structure also has to be braced in the other direction. It can twist, so the floor is bracing the floor. Each floor is also bracing the structure, if you like, from a horizontal deforming. Okay, a bit like going back into that illustration of torsion. So this is not a pinwheel structure, but here's next time you look at a building site and you think, hold on a minute, okay, here's the columns. They're not exactly square, but they're fairly squarish, and suddenly you come across this big solid concrete blocks. What are they doing? It's not because the load is suddenly heavier at this point. This whole element is bracing the structure from lateral load in either direction. There'll be one in this direction, there'll be one somewhere else in the other direction. Can't remember why I put this drawing up, but it's just a wonderful Willie Alsop building in Montreal in Canada. Of course it's a self-bracing structure because the columns themselves are already triangulating and therefore bracing the structure. You will often see in industrial buildings this kind of visible structural form, which again I say it's useful, I think, for us to help us understand how buildings are put together. Of course, now that you begin to look at these kind of buildings, you'll see these triangles everywhere and you'll understand exactly what they're doing. Just to remind you, we're talking about imposed loads. Snow can be quite dramatic. Okay, so the final part of this discussion of structural physics involves maintaining buildings with a center of gravity. Anybody who's ever played the game of Jenga will understand this problem. You have to keep the forces going centrally through the structure and not deviate too much from that. The way we tend to do it, particularly in tall buildings, is to have a very strong core to those buildings and allow the building to wrap around that core. And in most cases it's fair to say that these cores are made from reinforced concrete. And what you're looking at here is although it is, of course, it's a lift shaft, or it's a lift and stair shaft, and it also carries services up and down the building, so it functions in that way. But what you end up with is four big shear walls which are acting like continuous columns in the pinwheel that we looked at earlier on, that give an enormous amount of stability to the center of the structure. Here we are again, where the main lift core is providing the stable element at the center of the building. That happens to be the core of the Shard as it was being built, which is quite interesting. There it is again. The Shard is the Renzo Piano triangular, slightly triangulated building on the South Bank in London. So here is a kind of quite useful little tip for various ways of keeping high-rise buildings stable under load. that have been devised over time. You may, of course, invent something new yourself, and we hope you do. I will place this as a separate image onto Blackboard, so you can sort of download it or print it and put it on your wall above your bed, so you look at it every day, which is quite useful. I'm not going to go into each of the different types, but you can read about that later. That's for medium rise structures, and this is the same again for high rise structures. It's quite interesting to note that what you can see, most of what you see here are effectively simple beams and columns, if you like. There's some particular triangulation going on here and here, as you can see. There's very, very continuous and tight series of columns in this one here with the central core. This would pretty much be the design of the World Trade Towers in New York, that were very sadly the subject of terrible disaster in around about 2001, I think it was. And the reason that the building collapsed with a high impact, of course it's not the kind of impact one normally expects, but the reason it collapsed was called what we call progressive collapse, if you like. So once this floor section had kind of burnt out and the columns in it had began to fail, it collapsed onto the next floor. There were then the weight of 2 floors that then collapsed onto the 3rd floor, and so on, and the weight increased and increased and increased. There was progression until the whole building collapsed. This is if you like, a kind of solution to this. So it's an exoskeleton, it's continuous forces around the outside of the building. It doesn't rely so much on the central core with a series of outriggers, which we now know could fail, because if there was an impact at this level of this building, because there is a continuous triangulation wrapping around the whole structure, you could not get this sort of progressive collapse. Of course, what could potentially happen is that the whole thing would just fall down as one piece. It would topple. But let's not go there. This is a recent structure in Manhattan, in New York, by an architect called Raphael Vignoli. They call these pencil towers, and the reason they exist is, of course, because the developers being able to maximize profit from a very small footprint down at the bottom there. Of course, the higher you can go. Why are they stable with such a small footprint and such a ratio of height to the footprint? For 2 reasons. One is, although you can't see it, there is a continuous sheer external wall. So there's a kind of wall within the wall. There is, of course, the lift tower down the middle. But another little clever trick is you can just about see every so often there's an opening. These are, I suppose they probably call them gardens in the sky or something fancy like that. But what they're actually doing is, of course, they're allowing the wind to penetrate, so that at no point is the wind load impacting on impacting on more than just that section there, and that section there. So allowing the wind to actually penetrate the building rather than impose its full load upon it is important. Now, of course, we've known about this a long time. It's the reason why you'll see lots of fences and so on and outside and in exposed positions having little gaps in between them. It's not because it's pretty or anything. It's just to allow wind to pass through and not to impose too much of a load on that plane, if you like. Having said all that, a great deal of fun, and actually kind of something that architects have used and have had to use for certain reasons over a long period of time, is this idea of the cantilever principle. Cantilever is simply, if you like, something that leans out beyond the normal center of gravity. This is an interesting illustration because it's the 4th rail bridge in Scotland. It was built, I can't remember how many years ago now, but quite a number of years ago. A very beautiful structure. If you look at the photograph, you'd think, it's a series of arches, isn't it? That's how the structure's working. There's an arch here, there's an arch here, and we kind of know how an arch works. That one leans on that bit and that leans back on that bit, and it forms an arch. Well, of course, no. When you look at the building, the actual structure being built, you can see that what we've actually got is we've got a core structure here, and we've got 2 arms, if you like, that are springing from that core, that are cantilevering off that core. Now, because that's the same, oh, beg your pardon, I wasn't meant to show you that yet. Because that's the same mass as that, they're counterbalancing each other. The two sides are the load, dead load on that side and the dead load on that side are equal, so the structure is balanced. So in fact it's a series of independent cantilevered structures, and these are just little links, little trusses that are connecting the two together. They are not part of the overall structure. They are little miniature bridges, if you like, connecting the main bridges in the structure. Yes, well, there's an interesting, that's me by the way, that's Will McLean, and that's our glamorous assistant. The designers of the Forth Rail Bridge set up this model, and they called it the living model, to explain how the bridge, this cantilever principle, worked. And we recreated it. We thought it might be an interesting thing to do. So what have we got here? We've got, I think it's 40 litres, two 20-litre cans of water, 40 litres of water. As you know, a litre of water is a kilogram, so 40 kilograms there, 40 kilograms there. Our glamorous assistant weighed, I think, 58 kilograms, so we're well in there. There's pure tension. My arms are in pure tension. This element is in compression. Obviously it's pushing back down here, because if it wasn't there my arm would drop immediately. So that's in compression. Of course my legs, well, if I was standing, my leg, but this all of the seat is in compression. That's in compression again. That's in tension. She's hanging in tension off a compression element. That's the little bridge that connects the two parts together. A living model, very elegant way of describing the principle of the design. Of course, every crane is a cantilever. You now realize that. All the load that's coming down here is in pure tension. That's in pure compression. And that's equal on the other side. That mass here is equalizing whatever is the mass that is going to be lifted by the crane. There's some nice triangulation going on here. That, again, pure tension, back to that compressive element there. Compression, compression, tension. Same again. This is the canopy designed for the Ascot racecourse some years ago. This is then going to be covered in fabric, because it's just effectively keeping the rain off the punters, which are down here. But exactly the same thing going on. It's a cantilever principle. It's a truss, as you can see. It's not equal and opposite, is it? Because the mass of that is not going to be the same as the mass of that. So what's happening here is that this is tied back down into the structure, because this is wanting to push down this way. It's pulling that up. To stop pulling that up, it's tied back down here. Pretty much every large stadia that you go to will have some kind of cantilever in order to keep the visitors dry while it rains, and possibly in some cases to keep the sun off, without interrupting their view. So these big canopies are held, as you can see, as cantilevers, and very elegant again, because we can see what's in pure compression and what's in pure tension, can't we? Go back to the Forth Rail Bridge, the living model. These steel rods, tubes, I think they are rods actually, are in pure tension, aren't they? This is the big compressive element, and look again, you know, it's not just a simple one block of concrete with the same cross section all the way through. It's slightly tapering. And again, if you remember our original very first slide of a column going into compression, as the load pushes down, it slightly expands on the outside. If you design that into the column, you're sort of dealing with the forces right at the beginning. So that's very elegant. The column is already designed to bow very slightly, and that also gives it a kind of general elegance. And then there are always details. I often say about architecture and construction is that there's always the third element, if you like. There's a strut in tension, there's a strut in compression, but there's these critical things that you have to design as an architect to make it all work. Connection points. How do things connect? Especially when you're dealing with different materials. How to connect different materials. But that's another lecture. Won't go into that today. Yes, so there it is again. And as I say, you can have fun with it. Sometimes, as in that case, it's to solve a problem, to keep the rain off spectators. Sometimes it's just for a bit of fun. So that's what's going on there. We tend to call this a habitable truss. So it's that truss again. It's a deep, it's effectively one beam, isn't it? But it's a deep section now. Here's the triangular, here's the little tensile struts keeping the thing from deforming under any kind of load. And of course it's equally this slightly heavier steel structure at the center here, but the two wings of course are equally balanced, aren't they? Which is always critical to the cantilever. This is San Diego Calatrava in Palma, Mallorca. It's only a sculpture. It's that kind of engineers call it, I think, something like structural gymnastics. But actually, if we look at it now carefully and understand how it's working as a cantilever and what's in pure compression and what's in pure tension, we can see exactly what's going on. The load, of course, the load path is that these boxes, which are hollow, obviously not that heavy, although made to look heavy, the load part, all the loads are travelling down here and back to the, again, look, elegant, tiny little points of connection, triangulated for stability, the main columns. So all the mass of the structure is going back down to ground here. But of course what's stopping it tumbling is that this pure tensile element, which is way back here, where again the mass of the slab is transferred, the energy is transferred, isn't it? So the pulling there is transferred into this mass, which possibly even goes below ground, I'm not sure, but if it was a continuous slab it would also work, because it won't, if you're pulling that way, the slab cannot deform in that direction. And of course this just keeps these are in compression, aren't they? Or are they? No, hold on a minute. The top rails, these little rails, are pulling, but these are in compression, aren't they? Because as you pull down on, beg your pardon, as you pull on that, it's putting a force back into here, but you're still pulling on the top of the box, aren't you? So we understand it, but we also think it's rather clever. Here's another cantilever structure. This is pure. This is structural glass, and again that's another lecture, but I'm afraid you won't get it until early next year. But it is cantilevering. It's just an entrance to a subway in Tokyo. And here's some lovely drawings of it, just to show that it is pure. It is almost all glass, laminated, of course, for thickness and strength. More structural gymnastics. We know now, looking at this is actually housing in Madrid. We know now, don't we, that what's lying underneath here, inside here, is a continuous truss. It's not just the floor, because if it was just the floor is going to fail, isn't it? We know that that is a continuous truss of some kind, probably with a triangle again, probably a steel frame with a triangle on each wall, on the outside wall, on that wall, and that passes through the structure and probably counterbalances on the other side, or is certainly tied down into this main body of the building, which might be heavier and concrete, to allow that to work. Okay, so just think that it's the whole structure, it's that whole depth. Talk about the span to depth ratio. It's that whole depth that is maintaining the cantilever. It is a lot of fun. This is a slightly blurry slide, which is a shame, but this is to me a very elegant building, because in this case it's the outside walls that are cantilevering. Again, go back to the Fourth Rail Bridge, you can see pretty much it's a pure concrete structure, isn't it? This repeats all the way around the structure, just connects at these points here. So the floor loads, the floors here are all being carried by these facades, these concrete facades are doing the job of carrying the floors. Okay, and in the end that's what we're doing. We're carrying floors and roofs in the air. That's what all of these structures are doing. But let's just look at one other little, okay, it's lovely to have this opening here. This is actually a school, by the way. It's designed as a school building. It's nice to have the porthole openings, but of course they're also taking mass away from the structure where we don't need it. So they're making the structure lighter. We don't need that to be solid concrete. You're triangulating already here. If you can see, there's a top rail. If you just reduced it to a series of triangles, you can see it's a little bit like the Fourth Rail Bridge. So you're taking away mass, which is always a good thing. Take away the dead load. The less the dead load of the building, the better it is. There's another nice little cantilever, although it's slightly. I've never been convinced whether or not these old reproduction cast iron columns are necessary, or whether they're just part of or whether they're sort of decoration. But anyway, here's another beauty. This is actually before the London Olympics. This is in Crystal Palace, the only 50-metre swimming pool in London. Very beautiful pool, which I will show you in another category on some other day, I think. But there again, displaying very clearly the cantilever principle, but also displaying triangulation, structural stability. This is a cast concrete structure, but very minimal. It's very minimal. Look, even the little platforms themselves. Look, that's cantilevering, and each time it's tapering. All you need to do is triangulate, little triangulation. The whole thing triangulating. Each of these platforms triangulating. So what's going on here? It's not just that all the even the stair treads are cantilevering off this main structure here, aren't they? And they indeed are also tapering. So not only is it its overall structural logic is incredibly elegant, it's used the minimal amount of material to achieve what it needs. And in these days of sustainability and looking at how we use the world's natural resources, just thinking about the structure itself and how minimal and efficient we can be with structure, which engineers and architects have always done, just for the fact that you can do more with less. In these days of looking after our natural resources, it's become an even more important issue. And as you progress with your architectural education, this is something that you will have to pay more and more attention to. Where are your materials coming from? Where are you sourcing them? How can you be as efficient as possible with them? Yeah, there it is when it was built back in the day. And there it is now. Yes, you can tell I'm slightly obsessed with it, but the building itself is astonishing, but I won't show you all of that today. Yes, thank you very much. Good night, and we'll see you hopefully this time next week.